Yeah. Yeah. Can we get started? For those who are online, shall we get started?
Okay, sir.
Yes. So, yes. One minute. Listen. So the next chapter is moving charges and magnetism. Okay. So as the name suggests, right? When we have charges which are in motion, right? They create magnetism. That's what the whole objective of the chapter is, right? So just to give you So, to give you an introduction to this chapter, let's try to recollect from the beginning. So, first, what we discussed is about charges. So, when you talk about charges, right, they can either be in rest or in motion. So, when you talk about charges, whether they are in rest or in motion, there will always be a field called as the electric field around it. So I repeat, wherever you see the word charge, by default, one thing should come to your mind. What is it? Electric field, irrespective of whether it is at rest or in motion. But if the charge is at rest, there is one field that does not get generated, which is magnetic field. So if you observe, when the charge is at rest, there is no question of magnetic field. Whereas when you put the same charges into motion, then magnetic field gets generated, right? So having said this, the whole objective of the chapter is to understand the magnetic effects of electric current. Means how much is going to be the value of magnetic field that an electric current is going to generate due to a conductor. Okay. Second, whenever you talk about magnetism, there are two types of magnetism that can come into picture. One is permanent and the second is temporary. So when I talk about permanent magnet, those are the ones like bar magnets, horseshoe magnets, which you can go and purchase. And you see at any point in time, they are going to exhibit magnetism in the sense they will be able to attract the ferromagnetic substances. Whereas, so don't worry about ferromagnetic substances, we'll see in the next chapter. Okay. So as of now, ferromagnetic means something related to iron. So what is happening is, if you buy a permanent magnet, just take it close to a ferromagnetic substance, they start getting attracted. Okay, that's going to happen. Whereas when you talk about a conductor, when you just take a conductor, if you take that conductor close to a ferromagnetic substance, nothing will happen. Whereas you take the same conductor and connect it across an external potential difference source, then once the current starts passing through it, it will be able to exert a force on the ferromagnetic substances because there is a motion of charge that is taking place inside the conductor in an aligned way. Because of connection of potential difference, there is an aligned motion of the charged particles taking place, which in turn will generate magnetism, right? Which in turn will generate magnetism, and that will exist as long as you connect that potential source to it. The moment you remove it, right, magnetism is going to get lost in it. Right? So based on this, when I talk about this magnetism, right, there can be two types. One is permanent and the second is going to be temporary. So when you talk about temporary magnets, they are basically generated due to the electricity. Since electricity is used to generate magnetism, these kind of temporary magnets are called as electromagnets. So in this chapter, our objective is going to be only about electromagnets, and in the next chapter, we'll be learning more about permanent magnets. So that is why this chapter and the next chapter both are related to magnetism. But the only difference is here, who is generating magnetism? Current carrying conductors are generating magnetism. In the next chapter, what we will see is how do the permanent magnets have natural magnetism within them. Is that point clear? Right? So make a note of this. Those who are online, am I clear?
Yes, sir.
Sir.
So make a note of it. So let me know once you're done with this. Done? Okay. Yeah. Electromagnetic waves. That's called electromagnetic radiation. Radiation is a form of energy. இது வந்து சரி நீ கேட்டனால சொல்றேன். There are three things that come into picture. One is rest, second is motion. Motion can be further subclassified into two types: uniform motion or accelerated motion. So if the object is at rest, there is no question of magnetic field. There is only electric field. Okay. Whereas when you talk about motion where it is going to be uniform, it will have electric and magnetic field. Okay. Whereas if you put the same charged particle into an accelerated motion, there also you will have electric and magnetic field. But அதுக்கு பேர் வந்து electromagnetic wave ன்னு சொல்லுவோம். Why we call it as electromagnetic wave is because in the previous two scenarios, that is in the case of rest and uniform motion, the electric field and magnetic field will have uniform values. At a particular point, the value will be uniform. Whereas when you put it into acceleration, those values will be time varying. So if you're able to generate time varying electric and magnetic fields by putting a charged particle into oscillation, then you generate something called as electromagnetic wave, which you call it as a radiation. Radiation is a form of energy, that's it. Right? So radiation, it is a form of transfer of energy from one place to another. Last year you would have learned about this. Conduction, convection, and radiation. That happens in thermal properties of matter. So conduction means it happens in solids, convection happens within liquids and gases, that is fluids basically. Radiation, you don't need a medium. So energy gets transmitted from one place to another without the help of any medium. Okay, they are called as non-mechanical waves as well. Shall I proceed? Yeah. Listen. So since our interest is about finding the magnetic field due to whom? Due to a current carrying conductor, then we need a law to understand how these values can be calculated, which is framed by two French physicists. And what is the name of those two French physicists? They are called Savart. Okay. So when you talk about this law, they try to give a mathematical expression for finding the magnetic field due to a current carrying element. Listen to this carefully. They gave the expression for current carrying element in such a way that if you take this to be the conductor, let's say the current is flowing in the upward direction. So this whole part is called as a current carrying conductor. Okay. And due to this conductor, what I'm interested is to calculate the magnetic field at a particular point P. So I'm interested to calculate a magnetic field at a point P. But the problem here is I cannot calculate due to the whole conductor at a stretch. Rather, I'll be able to calculate due to an infinitesimally small element, which is called as current carrying element. So I want you to have this point in your mind clearly. This whole structure is called as a conductor, and the small portion is called as current carrying element. If I take the length of the current carrying element to be dl, then from the dl, if I take the distance to this point P as r, what did I do? From the current carrying element, I took the distance to the point P as r, and if I take this angle to be theta, right? So if I take this angle to be theta, then the magnetic field due to this current carrying element is, we're going to have a mathematical equation which I'll tell you now. Listen. The symbol used for electric field is capital E, and the symbol used for magnetic field is capital B. Okay. So this B is the symbol used for magnetic field. Now what I'm going to do is, since I need to calculate the magnetic field due to the small current carrying element, I will say that the value of magnetic field is dB, not B. What do I mean by the dB? It is a differential value. It is an infinitesimally small value, because this is also a small element. So this dB is observed to be, that is the intensity of magnetic field due to this current carrying element at point P is observed to be directly proportional to the amount of current that is flowing through this conductor. Okay, it is observed to be directly proportional to the length of this current carrying element. It is directly proportional to the sine of the angle between the current carrying conductor and the distance. I repeat it, it is not directly proportional to the angle, rather it is proportional to the sine of the angle. And it is observed to be inversely proportional to the square of the distance from the current carrying element to the point where you're trying to calculate the field. So these are the 4 parameters on which the magnetic field due to that small element is dependent on. Is that clear? They'll give you. Yeah. Irukadu. I'll tell you later. Okay. See, dB is directly proportional to I, dB is directly proportional to dl, and dB is directly proportional to sine theta. Okay. So point to be noted here is, whenever you talk about the angle between the current carrying conductor and R, you should always take it like this. You take the direction of current from the current carrying conductor, you will turn towards R in the shortest direction possible. What will you do? From the direction of current, you will turn towards R in the shortest direction possible. That angle through which you're turning is what is going to be the theta. Okay. See, because this could be theta, I could have taken it at the bottom also. That's not how it is taken. It is not because it is acute or obtuse. That's not the question. It is about the question of which direction the current is. From the direction of current, how are you turning towards R is what the question is. I hope I'm clear. Right? So these are the 4 proportionality terms on which magnetic field is dependent on. So when I combine everything and write it, I'll get dB is directly proportional to I dl sine theta the whole divided by R square. Right? So when I remove the proportionality symbol, I'll be able to write it as dB is equal to mu naught divided by 4 pi into IDL sine theta the whole divided by R square. Okay, where this mu naught divided by 4 pi has a value of 10 power minus 7. I'll come to the unit. Okay, it has a value of 10 power minus 7. And second point to be noted is mu naught is called as the permeability of free space. It's called permeability. Epsilon naught is called as permittivity. Here it is called as permeability of free space. So whenever you use a subscript of naught, it is related to free space. That's what we need to understand, because you'll be seeing something else called as only mu, which is just called as the permeability of the medium. So here what am I speaking about? It is only for free space. Okay. Now I need to answer one question of what is the unit of this? Does it have a unit or does it not have? So we'll see. So I told you that the symbol used for magnetic field is B, and the SI unit for magnetic field is going to be capital T, which is anybody? which is Tesla. Nikola Tesla. So it's derived from there. Since it's a name of a scientist, it's written in capital T. Okay. So magnetic field is measured in Tesla, right? So left hand side is Tesla. I need the unit for mu naught by 4 pi. This is Tesla. R square goes to the other side as meter square divided by ampere, meter, and sine theta does not have any unit. So meter and meter square get cancelled once. So you are left out with Tesla meter per ampere. So the value of mu naught by 4 pi is 10 power minus 7 Tesla meter per ampere. Is the point clear? So this is all about Biot-Savart law in scalar form. So till now, whatever I explained is only the scalar form. Okay. So why I am calling this as scalar form is, listen, magnetic field is there, no? Let's try to connect it to electric field. Electric field, is it a scalar or a vector quantity? Electric field is a vector quantity. Similar is the case with magnetic field also. So first we saw the intensity of it, then we are going to see how to write it in the vector. Okay. So make a note of it. It's for show. I'll call Vas. Done with this? Yeah. Listen. So, since we understood that magnetic field is a vector quantity, right? We need to understand the direction of it, right? Question is, when I talk about a permanent magnet, we have some tests using compass, right, or some iron particles and find out what is the direction of magnetic field. So using that, you would have understood that the direction of magnetic field is from north to south outside the magnet and south to north inside the magnet. So unlike electric field, where electric field starts with a positive charge and ends with negative charge, what happens with magnetic field? It forms a continuous loop. So this is with respect to a permanent magnet. Now, is there a solution for us to find the direction of magnetic field due to a temporary magnet? Okay, that is a current carrying conductor. Suppose I have the current flowing in this direction, right? Suppose the current is flowing in the upward direction. Then we have a rule named as right hand thumb rule, which can be used to determine the direction of magnetic field due to this conductor. So the concept is very simple. You take this conductor. For a conductor, if the current is flowing in the upward direction, okay, all that you can do is take your pen, just hold it in such a way that the nib is in the upward direction. So that is the direction of current, right? All that we need to do is, as the name suggests, take your right hand, place the thumb of your right hand in the direction of current, and curl the fingers of your right hand as if you're holding the conductor. What do you do? Left-handed. So take your right hand, place the thumb in the direction of current, and curl the fingers as if you're holding it. The direction in which the fingers are getting curled gives you the direction of magnetic field. Now we are clear with one thing: magnetic field can form closed loops. So that whole circular part due to this conductor will be the direction of magnetic field. Is that point clear? Right. So when you do this, in the example that I've considered, the current is upwards. So I place my thumb in the direction of current. See, mostly what will happen is, since you are looking at your book, right? Mostly, say I'm writing on this board, you'll be looking at your book, no? When you write it on the book, all that you do is place the thumb in the direction in which the diagram is drawn. After you place it, just curl your fingers, right? You need not completely try to curl. You just do it in such a way that wherever your fingers are going and hitting the book, at that point, the magnetic field is into the plane. So wherever your fingers are going and hitting the book, at that point, the magnetic field is into the plane. So to put it simple, in this case, what will happen is, right? In this case, what is going to happen is, since the current is upward, right? If I look at it vertically, I curl my fingers so that my fingers are going and hitting the board. So at that point, my fingers are trying to enter into the plane of this board. So what I will do is, I'll put an into mark and a circle around it, so it is understood to others that you are trying to say that the magnetic field is into the plane. So this is the symbolic representation instead of you writing in a statement. So into and a circle represents into the plane. So with respect to magnetic field, one advantage is, if you have found the direction of magnetic field on one side of the conductor, exactly on the other side of the conductor it will be in opposite direction. Why is it so? Because see, when I do this, my fingers are first going into the plane, and on the other side they are coming out of the plane. Obvious, right? So when this side it is into the plane, this side will be out of the plane. Just put a dot and a circle around it. So dot with a circle around it means that it is out of the plane. So this is a symbol that is used to represent into the plane and out of the plane. I want to stress on one point here. This into mark and dot is not used only for magnetic field. It can be used for any physical quantity which is directed into the plane or out of the plane. It is a general notation. But mostly what happens is, since in this chapter we'll be talking about magnetic field, we'll be using into and outward here. So don't get confused. Is the point getting registered? So just to summarize, what are we supposed to do in the right hand thumb rule? First, take the thumb of your right hand. Most of them will use left hand. I don't know why. I've seen that happen. So take the thumb of your right hand, keep it in the direction of current. So do one by one. Don't do everything at a stretch. Don't keep doing like this. Okay. So first place the thumb and then curl your fingers. So when you curl the fingers, the direction in which the fingers get curled gives you the direction of magnetic field. So to make it simple, see which direction your fingers are going and hitting the paper. So wherever it is going and hitting the paper, there put an into mark. On the other side, by default, put a dot and a circle. It will be out of the plane. Is that clear? So this is all about the right hand thumb rule. Okay. Can make a note of. Clear? Those who are online, are you clear?
Yes, sir.
Yes, sir.
Good. force பத்தி கவலைப்பட வேணாம். force கூட இதை யூஸ் பண்ணும். அதனால அதை பத்தி கவலைப்பட. whatever I explained, you are clear. எப்படி யூஸ் பண்ணனும் தெரியும்ல. அதுக்கப்புறம் நான் பார்த்தேன். I will explain in wherever you need to apply. அதை நான் பார்த்தேன். Okay. Should I proceed? Yeah. Okay. So the next question is, we understood that the magnetic field has direction, and we understood how to find the direction for a current carrying conductor using right hand thumb rule. Now the question is, we have seen Biot-Savart law in the scalar form. How are we going to represent the same in the vector form? Okay. So listen. If I take the conductor here, the current is in the upward direction. I take a small element dl and a point P here. From the dl to point P, let me consider the distance vector. Okay, let me consider the vector r. Now, I want you to focus here. Listen. Whenever you are taking this r as a vector, no, you need to always consider the current carrying element as the initial point. Because whenever you are representing vector, you need to have a starting and an ending point. Here, what will you do? You will consider the current carrying element to be the starting point, and the point where you are trying to calculate the field to be the ending point. First point to be noted. Second, if you observe current has direction. Current has magnitude and direction, but it is not a vector point. If you observe dl has magnitude but no direction. So there is a tricky problem here. Now, how to solve this is by considering I and dl together. So what will you do? You will consider I and dl together, so that you will write it as I dl vector, where the direction of ideal vector is going to be the direction of current itself. So the direction of current is going to be the direction of ideal vector. Similarly, r vector is going to be directed from where to where? Directed from dl vector towards the point P. Are you able to understand this? Are these 2 points registered? Now, if I look at the scalar part of it, dB is equal to mu naught divided by 4 pi into ideal sin theta divided by r square. So remember, by now we should have understood, since we used right hand thumb rule and we are trying to use vectors here, there is some product that is going to help us to convert it to a vector form. So what product am I supposed to use? Obviously, cross product, right? That is why you have sign also here. So you're going to write it in terms of cross product. But for me to write it as cross product, I need 2 vectors. If I observe this expression, I have ideal together is 1 vector, and I don't have any other vector in the numerator. What is the other vector I need? R. So for that, what I will do is I will multiply and divide it with R. Right? When I do this, I get mu naught ideal into R multiplied with sin theta, the whole divided by 4 pi into R cube. r square into r cube. Now comes an important question. I have ideal as one vector, r as another vector, and I have sine theta. So it is obvious that I need to write the cross product between these two vectors. But the tricky part here is a vector cross b vector is not the same as b cross a. So I need to know whether I should write ideal cross r or r cross ideal. So which one should I write? So I cannot just like that decide, just because I wrote ideal first, I cannot write it as ideal cross r. I could have written r also first, then it will not be r cross ideal. We don't know which one is right. So for that, we need to connect two dots. The two dots that you are going to use is cross product and right hand thumb rule. RHTR is right hand thumb rule. So I need to understand cross product and right hand thumb rule. I need to connect both the dots. So observe this carefully. So when I talk about cross product, right? If I'm doing a vector cross b vector, if I do a cross b, then what I need to do is I need to keep the second vector fixed. I need to keep the second vector fixed. From the first vector, turn towards the second vector in the shortest direction possible. So from a vector, if I'm turning towards b vector, I'll go in the anti-clockwise direction. Okay, is this point registered? Now the question is, you will again use your right hand, but exactly in the reverse order of what you saw in the right hand thumb rule. So in right hand thumb rule, what did we do? We first place or fix the direction of thumb and then curl the fingers. Here we'll curl the fingers and then extend the thumb. So observe, a vector is like this, b vector is like this. In this case, if I do a cross b, it is anti-clockwise. So it is telling me take your right hand, curl the fingers of your right hand in anti-clockwise direction and extend the thumb. So when you extend the thumb, a vector cross b vector is there, no. So if I write it as c vector, then that c vector is facing towards you. C vector is towards you. So towards you means what will you put? Dot and a circle. It is out of the plane. Similarly, if I do b cross a, I'll get into the plane because they both are opposite to each other. I'm not going to do b cross a. So if I find the cross product for one, I can find the answer for other easily. I'll just put a minus sign, reverse the direction, and done. So this is with respect to this logic. Now what I need to do is, I need to apply the same cross product here and do this test and see to understand what is the direction of magnetic field. So first, let me use right hand thumb rule. By using right hand thumb rule, can you tell me what is going to be the direction of magnetic field at P? Right hand thumb rule means first thumb and then curl fingers. So thumb is upwards, curl the fingers are going and touching the board. Wherever it is touching the board, it is into the plane. So right hand thumb rule is telling me that the magnetic field at point P is into the plane. So what should the cross product do? Cross product should also be done in such a way that I get the resultant in the direction into the plane. So for that, what I need to do is, if I write ideal vector cross r vector, listen to this carefully again. Ideal vector cross r vector. What are we supposed to do in the case of cross product? Fix the direction of second vector. From the first vector, turn towards the second vector in the shortest direction possible. So ideal is upwards, r vector is fixed here. So since r vector is like this, from ideal, which direction should I turn? From ideal, I need to turn in the clockwise direction. So when I turn in the clockwise direction, this clockwise is telling me that take your right hand, curl the fingers of your right hand in clockwise direction and extend the thumb. It is going into the plane. So I should only write ideal cross r and I should not write it as r cross ideal. Why is it outwards, sir? Because you know how you understood a cross b? What are you supposed to do? In a cross b, which is first vector, which is second vector? B is second vector, no? In ideal cross r, who is second vector? R, no. Fix the direction of R. Yes, from the first vector, turn towards second vector in y clockwise. I told you I was stressing on one point, shortest direction possible. So I have to go clockwise. So clockwise, it is into the plane. So cross product is also giving me into the plane. Right hand thumb rule is also giving me into the plane. So I need to write it as ideal cross R. I hope you got the answer. It is not because I wrote ideal first, I should write it as ideal cross R. Okay. So this will be equal to mu naught divided by 4 pi into ideal vector cross R vector, the whole divided by R cube. Listen to this carefully. The last point to be noted here is when you write it in the scalar form, the denominator is going to be R square. Whereas when you directly write it in the vector form, the denominator will be R cube. Okay. And the second thing is, this is what is dB with a vector symbol on top of it. So dB vector is equal to mu naught by 4 pi into ideal cross R divided by R. This is the vector form. Okay, this is a vector form for magnetic field. Due to whom? Due to a small current carrying element. It is not due to the whole conductor. It is only due to a small element. So for the whole conductor, if I need to integrate it. Are you able to understand this point? So listen. If at all they frame an MCQ based on this, there are four ways. There are four options that they can give you, right? So one, they will give you ideal cross R by R square, ideal cross R by R cube, R cross ideal by R cube, R cross ideal by R square. So which one is right? Ideal cross R divided by R cube. This is what you need to be clear about, because all the options will look similar. They will confuse you. So first thing is, you need to remember ideal is first, R is second. Second thing that you need to remember is denominator is not R square, it is R cube. In which form? In vector form. Yeah. So make a note of this. புரியல. Into one என்ன into dot or cross. Okay. Will be ABC. AB sin theta n cap. And n cap is a unit vector. It's perpendicular to both the vectors. Clear with this? Okay. So let's summarize what we saw. First, we saw the introduction. Then we saw what is Bayes-Savart law, due to which you calculate in the scalar form, right? Due to which how did it help you to calculate the magnetic field due to a small current carrying element at a point P? So what is the formula? dB is equal to mu naught by 4 pi ideal sine theta by r square. So how should you consider the theta to be? Theta should be considered in which direction? Not shortest direction. From ideal, you need to take a turn towards r. That can be anyway. Okay. So that's the second thing. Next, we saw what is the right hand thumb rule. So what is right hand thumb rule tell us? Extend the thumb of your right hand in the direction of current. Curl the fingers as if you are holding the conductor. So the direction in which the fingers are wrapped gives you the direction of. Then we saw Biot-Savart vector form. So if you consider this to be a derivation, in the derivation, what are the two dots to be connected? Understanding cross product and right hand thumb rule. So we need to ensure that they both are in sync. Right. So once you validate all those things, what is that you get? dB vector will be equal to mu naught by 4 pi into ideal vector cross r vector divided by r cube. Right. So after this, the next concept that we are supposed to see is start applying this. That is applications of Biot-Savart law, for which we need to calculate the magnetic field due to a straight current carrying conductor of finite length. But that will take at least half an hour for me. Okay. So since I started the basics today, next class I'll start with those derivations. So I'll be explaining two things of finite length. From there I'll take you to infinite length and then we'll solve some problems. So next class fully we'll learn only one concept because it is that long. Okay. And secondly, I need to teach you some bit of integration. Because I've been telling you from the beginning, you will take DL, then you need to integrate to get the value due to the whole conductor. So I'll be teaching you some part of integration as well. We'll go hand in hand. Okay. So we'll start that on Monday. Clear? So any other questions from today's class?
No, sir.
All clear? Okay.
Yes,
No,
sir.
sir.
Yeah.
Yes,
So
sir.
we can wind up this.
Thank you, sir.
Thank you, sir.
Potential developer syllabus program, civil engineer getting. Alright, medical needs for. That's the. Right, if you're not able to take up the rest, please go before me. And wrong person. That's already looking for. Go inform me. And this is the number for the. Number this number. So basically the total form, right? நான் தான் போட்டேன் இது நல்லா தான் இருக்கு அதான் சொல்றேன் பேக்கே நல்லா தான் இருக்கு